Thanks, everyone. Thanks for coming to the talk. My name is Ken. I'm the VP of Engine at Rad AI, and this is my colleague Priunsh. He's a senior MLOps engineer. We also do recognize that I think after this is like happy hour or something like that. So, I hate to be the person standing between you and your preferred drink, alcoholic or not. So we're going to try to make this more engaging and more interactive as possible. And please ask questions as well. So we're here to talk about how we can apply ML and Ray to radiology. So first, why radiology? As we all know, the population is aging over time. Medical technology is advancing, and humans have much higher life expectancy. One of the side effects of having higher life expectancy and living longer is you start having more problems that comes with age. You start needing more scans, whether it's X-rays, MRIs, brain CT scans, etc. In this chart, which was, we got it from the Department of Labor, we can see that the demand of radiology has increased far more than the increase in radiologists. We are not producing enough radiologists to match the demand of what the US needs from radiology scans. What does that mean? That means we have a burnout problem. Radiologists are burning out. That means we cannot read enough studies. We cannot serve all the patients that need to be served. And we have a huge backlog that we just cannot process. So this problem, we believe, can be solved with AI. Let's talk about our first product. Our first product is called Rad AI Omni. So in a radiology report, what a radiology does is they go to a dark room, sometimes in a basement, sometimes not. It's a super dark room with like 3 or 4 monitors. They look at an image, and then they dictate into the void, into the abyss of what that images represent. The way they dictate has to follow a specific pattern, the pattern of the radiology report. The radiology report has different sections. There's the finding sections, which is all the observations they see. And then there's the impression section, which you can think of as conclusion / recommendation or diagnosis. In a normal workflow, they dictate through all of their findings, both the positive and the negatives. Basically, you can think of it as they have to go through every single pixel of the image and talk about how this is normal, this is normal, this is not normal, I see something here, I don't see something there, and go through everything. And then they dictate the conclusion and the diagnosis section, which is the impressions. What we started out doing, is we can automate the impression section. Why is the impression section important? Because when you're a doctor and you're ordering a patient to do radiology scans, 90% of the time, you don't actually read the report. This is a small fun fact, and I might offend any physicians here, but 90% of the time, they don't read the report. They go straight to the impression section, read the TLDR, and then move on. Right? Most of you are probably engineers here. You probably don't want to read through the entire document. You go to Stack Overflow, you read the TLDR, and you move on with your life. Maybe you know how it works under the hood, maybe you don't know. If you can get things through, if you have a lot of work, if you're behind on deadline, you just want to move on. Most doctors only look at the impression section, and that's why it's important to make sure this part is automated with high quality. Now, again, to recap, what do? We generate the impression section. We can actually customize the generation on a per radiologist basis. So a radiologist that's trained in Harvard and one that's trained at Stanford can actually write their impressions in different styles using different words to represent the same meaning. And finally, we also include consensus guidelines. What is consensus guideline? It means I might recommend someone, given the findings, and say, hey, please come back 3 months later for a CT scan. In the current world, a radiologist would have to look up the consensus guideline, which is a bit like a dictionary, a book, and then dictate it back in. What we do is we can ingest the consensus guideline and add it onto our impressions automatically. So let's look at a demo. So all this sounds very abstract. Let's look at a demo. Over here on the left-hand side, what you see is a radiology reporting solution. You can see that there's different sections. There's the findings, methodology, impression section. To make the demo a bit faster, we actually pre-populated the findings section. Unlike most doctors, the reporting solution is the main software that the radiologist is operating on. they don't actually go into the EMR, electronic health record, that much. They actually stay in this solution. On the right-hand side, you can see there's Rad AI Omni. This is a zero-click solution. What it means is once you have it running in the background, it automatically integrates with our reporting solution, and it will automatically trigger. As long as your automatic mode is on, as you can see in this, it automatically triggers. It takes about 2 seconds, and it generates the impressions down there. You can probably see that the impressions down there are not made up. Right, the RV-LV ratio is about 1.6. You can see that reference in the impression section as well. Those of you who have really good eyesight can actually try to check. We marked the ones in green, just the key ones in green. You can check. Those are all reflected in the proper specifics in the impression section. This is really important. We need to make sure that the impression section is highly accurate, and we also need to make sure it's actually customized to the radiologist style. The next thing is that we are not here to replace radiologists. Think of us as a co-pilot for radiologists. So ultimately, the radiologist is always in control. They can actually go in and add and modify the impressions before they sign off on the report. So what we do is we're a productivity tool. We help them generate the impressions automatically, save them the time, and then they can then ultimately decide how they want to modify it before they submit it back. The cool thing about this product is that when they modify things, we can then ingest that information back into the next round of our training. Think of it as a modified RLHF, if you will. We can then take the signal from the radiologist, how they modify the impressions, bring it back to the next round of training data. Now, why are we satisfied with just Omni impressions? You might ask, can we actually automatically generate the full reporting? Well, I'm glad you did ask, or in my mind, you asked. That is what we're doing next. Recall our, what is the new workflow here? Instead of dictating the full report word for word, they can actually just dictate key findings or even deltas between the last report and the current report, and we can then automatically generate the full report for them. They can then review it, sign off on it if it looks good, or make some small adjustments to it. So instead of just saving them the impression section, we can save them the whole reporting section. So we can free up the radiologists to do what they do best, which is interpret images, and we take the tedious, the more mind-numbing part of dictating word for word out of their workflow. Let's look at a demo real quick to see what it looks like.
Radiologists can dictate findings freeform into the Omnibox in whatever order they want.
Bibasilar atelectasis, period. Distended appendix measuring 11 millimeter with adjacent stranding but no abscess, period. 2 centimeter hemangioma in segment 3 of the liver, degenerative changes in the spine, period. 3.7 centimeter right renal cyst, period. 5.3 centimeter left ovarian cyst, period. Splenic granulomas, period. Status post cholecystectomy, period. Omni report.
Omni will organize those findings and insert them into each radiologist's personal template and automatically create the impression in their personal style.
So this is the first of the demo. In this demo, they actually dictate most of the findings, and then we put them into all the right sections of the report, and we generate them. Now, let's take a look at the second demo. This one is where you don't actually have to dictate the full findings. All you do is dictate the delta between the two studies. Most patients are repeat patients. You can actually look at the previous study, compare with the current study, and dictate the deltas. Let's take a look at this. The left side is a prior exam, and the right side is the current exam.
New right IJ catheter in the SVC period, feeding tube in the stomach period. Omni unchanged.
It takes a few seconds, and it can generate everything else based on all the prior reports and metadata.
Field comparison, 10/31/23. Field support lines. New right IJ catheter is in the SVC period. A feeding tube is in the stomach period.
This is going to take a long time. I didn't want to make everyone have to sit through this, so 3xing here.
Although superimposed pneumonia cannot be ruled out, period.
So as you can see, this is actually a pretty big difference. We can actually be 4x faster. We can actually save radiologists from burnout. And we can actually make sure that they can go through a lot more cases than they would in the past. So to recap, right now, for impressions alone, we generate 100,000 reports a day. So that's 100,000 patients that we're helping every day. There's about 4,000 radiologists in the US that's using our tools every day. For context, there's about 30,000 active radiologists in the US. And we can actually save them quite a bit of time. Reporting, which is our new product, we recently just launched this year. We currently signed with 5 customers, so some of the data is still not statistically significant yet. But so far what we see is we can actually save radiologists up to 90% of the words. And on average, it's about 3-second median time to generate the reports. So enough about the radiology context. We're here to talk about Ray and how Ray helps us. Here's a quick overview. What Ray does is it helps us with, especially with how we orchestrate tasks. The way we've organized is that every single model is its own Python project, and it's templatized. And those of you who are clearly experts in ML, you know that each of the ML features are not backed by just one model. Generally speaking, you need multiple models, some checking each other either during training or during inference, and they all need to work in sync together for a feature to work. And so what we do here is we can actually templatize the models, whether it's ETL, whether it's train, whether it's deploy. We can actually repeat all those things with the same template, and then we can run it. And one of the nice things about Ray is it can actually orchestrate the model training across multiple different models. We actually currently have models that rely on each other, and having Ray as an orchestrator helps us ensure that all dependencies are done in the proper way. And my colleague Priunsh is going to go through a lot more details on how we do this. Priunsh.
Hey, I'm the resident nerd at Rad AI. Thanks, Ken, for an overview of our products. I'm an MLOps engineer here, and I helped build the Ray infrastructure over the last year at Rad AI, and I'm here to talk about it. So starting out, I kind of wanted to talk over how our infrastructure has actually evolved over time. We were founded as a startup back in 2018. We're a startup today, and it's just interesting to see what was doable for us back then in 2018 isn't today, and how that just evolved over time. So let's go to 2018. So in 2018, we maintained an on-prem cluster, and we were training models in the range of around 100 million parameters at this time. And this is what it looked like. We had 3 V100 nodes literally in a server in Palo Alto. In fact, an MLOps engineer and a researcher actually went out there with cables to connect it to the network. And it was very raw when it came to actually just putting GPUs in hands of researchers. And for the most part, this is all that was really needed for a startup. And you can see that there are no abstractions around this. Essentially, researchers were essentially just SSHing into the machines. But that was really all that was needed to push the initial models into production. And you can imagine that without any kind of interfaces that this could occur, where a researcher comes in and asks, hey, I want to use GPUs 7 and 8, whereas the first researcher says, I want to use all 8. Well, because the team was so small, they could kind of just work it out person to person, and it wasn't much of a problem. And this is literally what shipped models in production back in 2018. But that was all that was needed. Then we come to 2021, where we entered the cloud scale. Now we were training models in the range of around 500 million parameters. So how did our infrastructure change? Well, we added the ability to scale GPUs in a cloud-native fashion. So here, researchers could now simply spin up VMs when they wanted additional capacity in their cluster. So not only did we have those on-prem instances on the right here, but also the ability to scale cloud-native. And again, this worked quite well. Now, we did have some interfaces in front of this. We used Puppet to deploy these VMs to account for authentication and things like that. So there was more than just, say, SSHing into an on-prem instance. But again, this was really enough for another year, year and a half. Eventually, researchers started asking the question, though, of, hey, can I double the size of the model? Can I quadruple the size of the model? And as an MLOps engineer, you get kind of worried. You ask yourself, does that infrastructure we built support it? They even ask, hey, can we one-up the magnitude of the amount of data we want to push through the model? Oh, and also our deadline is next week. Well, that presents some problems, and that's where multi-node training comes into the picture. So if you've ever actually done multi-node training natively on a cloud VM, it is quite complicated. Clouds support it natively, but in order to set the right variables, if you're working with deep speed, for example, you have to set like host files, the IPs, you have to run Python on each of the nodes and get them all to sync together. It's quite a complicated ask to ask a researcher to be doing all of this in the first place. So that was still a problem back in 2022. Now we enter 2024, where we're in the multi-node phase. We can train models in the range of around 10 billion parameters and more. We're using OSS Ray with Kuberay, and we also have cloud autoscaling enabled. So what does that look like? Well, initially, back in March, this is really all that it looked like. We put these A100 nodes into a Kubernetes cluster, and then we added Kuberay, which there are plenty of talks about this earlier in the day, but it is basically a Kubernetes operator that allows us to deploy Ray clusters on top of these GPU nodes. And what it did day one is allow us to orchestrate more than one A100 node to actually train our first production model that we pushed out back in March using this new Ray-based architecture. This is really all that was needed. And here's some of the data we collected when we initially did this train. So our validation loss actually went down, and this is because we could actually increase the batch size of the data, and therefore the model could see more data. Next, we actually reduced the time per epoch by about 3 hours. And then finally, time for comparable accuracy, which means that if we were to have stopped the train before it converged at a comparable accuracy to a single node, then we would have stopped it about 20% sooner. And you might be looking at this and ask yourself, hey, you doubled the number of GPUs, but the time for one epoch didn't go down by much. And the comparable accuracy also didn't go down by much. Well, I included this in the presentation specifically to call out the fact that when you scale from just one node, one A100, H100, doesn't matter, to two, you immediately incur a network bottleneck. And you have to keep that in mind, especially if all you're doing is going from one node to two nodes. In fact, today, when we train production models, we use at least 4 to 6 to 8 A100 nodes to make sure that we don't incur that initial loss in performance just due to that bottleneck. So back to our story. Although just Kuberay was enough to actually help us train a production model, it's quite hard to write manifests directly for Kuberay. If you've ever worked with it, it's a 200 line YAML file that you would ask researchers to basically fill out. What do you want for your head node? What environment variables do you want to set for nickel? There's just a lot that a researcher would have to manage if the only interface they had was Kuberay directly. So we did two things in the last couple months. One is we added Q, and another is that we added Rad Train. So Q is an open source job scheduler for Kubernetes that allows researchers to essentially request a certain amount of GPUs, say 4 GPUs, 8 GPUs, 16 GPUs, and it enters a work queue. And once their request gets to the front of the work queue, the cluster decides, hey, is there enough GPUs in our cluster to allocate this Ray cluster? And if there is, it'll be allocated. If it's not, it'll wait in that queue. And of course, with any queues, there are priorities and things and overrides that you can work with. But essentially, it's a way to queue up requests for resources. Additionally, on the bottom there, that line shows that Q actually integrates directly into our cloud's autoscaling layer. So researchers can explicitly request if our static cluster, which contains several A100 nodes, doesn't have enough resources, they can explicitly request autoscaling nodes. And the reason it's explicit is because autoscaling nodes are quite more expensive than the contracts that we have for our existing nodes or our static nodes. So that's Q. So as I mentioned earlier, you could work with Q and Kuberay directly. They provide a lot. However, this is where we entered into developing Rad Train because we wanted an actual interface for researchers to interact with these clusters instead of interacting directly with Q and Kuberay. So what is Rad Train? One, it's actually a play on Ray Train. We called it Rad Train because Rad AI, and what it does is it provides a cloud-agnostic description of a user's Ray cluster by GPU type. So here's actually all a researcher has to provide to create a cluster on the infrastructure I just showed you in the last slide. One is they just provide the Ray cluster's name, so here just training cluster. We use weights and biases for our model governance and artifacts. So here I provide my name, Priunsh Syen. Then researchers can provide exactly which ray cluster or ray version that they want. Here I have 2.30, but let's say there's some kind of improvement. Well, they have full control and they can actually upgrade it to 2.32. Or they can downgrade it if there was some bug introduced. They have full control there. Next, they can say exactly which GPU type they want to use as well. So here they have the A3 H100 type. A3 referencing the actual GCP type and A3 machine for these H100s. But there are also A2, A100 types, and then the auto-scaling equivalents of each of these. And again, the auto-scaling piece is explicit because auto-scaling is much more expensive than just going to create clusters on our static infrastructure. Next, they can specify exactly how many replicas they want and how many GPUs per worker or per replica that they want. So what this represents here is a 4x8 setup, 4 nodes with 8 GPUs each for a total of 32 GPUs that they can run this training on. And then finally, they can specify exactly which Docker image that they want to use to run on these worker nodes. Here, I just have the RayML image, which contains a bunch of libraries you would expect to have as a machine learning engineer, like Torch. But in production, we actually use properly built frozen dependencies, a properly built Docker file for training in production, not the RayML image. Additionally, RadTrade composes all cluster operations into a unified command line and Python interface. So here's a bit of an example of what you can do with RadTrain. There are all kinds of things. Of course, you can create a cluster, you can destroy clusters, you can forward to your cluster, you can create jobs, stop jobs, copy data to and from your cluster, start up Jupyter notebooks as you need. This is like the interface that our researchers use to interact with the cluster. And here's an example at the bottom here, radtrain cluster create, and all we pass in as an argument for most of these is just that YAML file that I talked about in the previous slide, -y, model configs, raycluster.yaml, and they can create cluster. Additionally, radtrain also promotes good workflow software engineering practices. So as Ken mentioned earlier, we follow Semver version packages. There's been a trend in the industry to go deploy directly from Jupyter notebooks, but we want to apply better software engineering practices and make sure that we're maintaining our models well, not just for the researchers that develop them, but the next researcher that comes down the line that needs to add a feature or retrain the model. Additionally, we Dockerize everything, so that dockerfile.gpu is the training Docker file that we use in production. Next, we use Poetry to make sure that we lock all of our dependencies and can manage them. And this includes PyTorch. I know there has been problems with PyTorch and Poetry if you're thinking this, but they have resolved them. And then finally, because we have this Python package first view on maintaining models, we can deploy CI/CD to this very, very easily. So hopefully this has given you a bit more about what's going on the right side of this, how RadTrade actually integrates with our ray cluster, and then also the left side of how we actually maintain models as proper Python packages, essentially. And additionally, what's going on in the center, which is because they're well-provisioned Python packages, that we can automate ETL, train, and deployment very easily. So you might ask, well, where do we go from here? Things are looking pretty good, at least. Well, I designed it, so I think they're pretty good. But we're going to an era of multi-cluster, and hopefully the diagram on the next slide will better explain this. But in this era, we're looking to train models in the range of around 100 billion parameters. Of course, that's an approximation. And then finally, we would like to make sure that our scaling is cloud agnostic. So what does that look like? Well, it doesn't actually look that much different than that previous diagram. But as you'll see, what's missing on the right is the on-prem instances that we do actually use for non-production use cases today. What we've done here in this diagram is actually deploy GKE bare metal directly onto those on-prem instances to bring it in essentially as just another Kubernetes cluster that our researchers can use to train on through RadTrain. And if it's starting to look like a template where we have GKE, our main cluster, GKE, bare metal, our on-prem cluster, so on and so forth, well, that was totally intentional. Actually, this is super relevant to healthcare specifically because there are certain restrictions on where we can take PHI, personally identifiable health information, in the world. So for example, in Canada, if we're wanting to train a multimodal model on images, MRIs, X-rays, that's considered PHI, and we cannot train that model outside of Canada's borders. And because this is essentially a template to deploy Kubernetes into other regions, well, we can do exactly that. We can bring up an A100 cluster in Canada to train that multimodal model. And that's true for other countries as well. The EU has its own laws, Australia, South America, Asia. There are plenty of laws that surround PHI. And the design of this infrastructure as a templated Kubernetes deployment is super important for that. And multi-queue will help with that too. We're running a little low on time, so we can perhaps save it for questions at the end if you're wondering what that is and how it helps. And yeah, that's it. Thanks. So let's take some questions.
Looks like.
So on your last slide, does this also allow you to train models in different regions without getting the data out of the region?
Correct, yes. So the idea is that because we've basically templatized the deployment of these GPU clusters, we essentially, I will say it's not as easy as saying US Central 1 to Canada Central 1. It's not going to be that easy. But the infrastructure itself is basically templatized. So yes. So for example, we did recently train a model in Canada, essentially doing this.
Okay, but it doesn't allow you to train the same model first in Canada and then further train it, basically.
Yeah, depending on the regulations of the country, sometimes you can't actually train the model.
So what we actually do, depending on regulation, is you can first train an initial version of the model in a particular region. What you can do is then you can just like copy and paste the weights over to the US region. So you don't have any PHI violations, but the weights are you're allowed to copy over. Then you can run either a lower adapter or run another second fine tuning or whatever you want to do to then train. And that's kind of how we can work around this situation.
Yeah.
Yeah.
What does your dependency management look like for different projects or algorithms?
Yeah, that's a great question. Part of the thing I did want to solve with RadTrain was not only just the RAID cluster side of things and orchestration, but also dependency management. And I think this structure of making sure that your models are their own Python packages is what makes dependency management relatively straightforward. So here, researchers actually have the ability to say, use the latest version of PyTorch when, say, another model has been outdated but is still in production, but there's no dependency between them. And they can update it as needed. So that's essentially it. We've isolated these dependency problems by just making sure that models are their own first-class Python packages. Yeah.
Question in the back.
Related to that, you mentioned you're using poetry. Like, were there any particular trade-offs that put you in poetry instead of like tools or
Sure. Yeah, that's a good question. So I have used poetry in the past for a while now, so I was a bit biased when also designing it, so I'm going to put that out there. You can come up with a workflow where you use pip tools and other types of workflow tools like that. But what I liked about poetry and what I still like about poetry today is that the workflow is fully end-to-end. It not only manages your dependencies and lock files, but also manages the virtual environments. So at least for adoption for the researchers, it was relatively straightforward to tell them to use just a single tool to do essentially everything, versus, say, cobbling together pip tools with pip and PyEnv and all these other things to get it working. So that's how I use poetry.
So I didn't completely understand your training aspect of it. You took the audio and then converted it into the radiology reports, right? You're not doing any image training on the radiology specialty, right?
Yeah, so that's a really good question. So there's two things that we're doing. First is we take voice and we turn it into text. That's the first thing. The second is we then take the outputting text, which is just a few bullet points, we turn it into a full a full report. So there's voice to text, and then there's text to text as well. We don't do imaging yet, and that's something we're exploring for the future.
So how is this different from medical transcription that happens? I'm
Yeah.
trying to understand.
So medical transcription, what they do is they convert your voice to text word for word. What we do is we take one step further. We not just converting your voice to text word for word is just step one. Step two is taking your words and then generating a full radiology report, right? That's not what the medical transcription workflow does right now. Right now, if you want to generate a full radiology report, you would have to dictate the report word for word. So imagine you're writing an article. you have to dictate each word for word in your article. What we do is you can dictate a few bullet points and we generate an article for you and publish it for you. That would be the analogy.
So there are services that do it for different specialties. Yeah, like the medical transcription. They don't do word to word, but they do convert it to very specialty things and which are not bound to the continent part. We can discuss
Yeah.
this offline.
Yeah, we can
Yeah,
talk
we'll talk
offline.
about
There's a lot of tools to go from voice to text, but for radiology specifically, I don't think there's any tools in the market that go from bullet point to the full radiology report. That currently doesn't exist in the market. Yeah. I think we're right on time, so thanks everyone. If there's more questions, happy to chat offline.
Yeah, so.